let's get started. So it looks like Leo isn't around here today, so I hope the streaming is working. I will not be able to monitor online questions for anyone who is watching the streaming, unfortunately, but we'll try to answer them after the lecture. So I haven't really done these biographies so far, but I wanted to start off here by doing one of them, because it's an interesting one. So maybe some of you have heard about Ada Lovelace, famous person in the history of computer science, sort of. Actually, her name was Ada King, after marriage, born Byron, to the poet Lord Byron. But she was the Countess of Lovelace, and hence the name. So her sort of claim to fame in computer science is that she wrote the first published computer algorithm, although there is some controversy among historians over how much of it she actually wrote. But she did make some very insightful comments about computer science. So she was interested in science and mathematics in general. I'm not sure to what extent she was formally schooled, just sort of homeschooled. And she was in some ways friends with this person called Charles Babbage. So you may have heard of Babbage and his analytical engine. So Charles Babbage was also a mathematician, inventor, generally a bit of a weird guy, but so he had built a machine for doing calculations. So this was commissioned by the English government at the time, because they wanted to do efficient calculation of logarithm tables, because those were important to doing calculations that had practical uses, such as calculating trajectories of artillery, which I think was one of the main practical uses. But after doing that, actually, if I remember, the story is a bit convoluted, but because he was, although he was perhaps clever, he wasn't a very good manager, so he got into a lot of fights and arguments with the people who were actually working for him and building things. So during sort of a break while work on his difference engine, as it was called, stopped, he sort of started making plans for a much better machine, which he called the analytical engine. And the analytical engine was intended as a general purpose computer. So it had, according to his plans, it had sort of two components. It had a store, and it had what he called a mill, which is the essentially the memory and the CPU. So it would be able to take values out of the storage, perform a calculation, and then put the values back into storage. And it will do this repeatedly according to a sequence of instructions that are fed to it, which tell it which values to retrieve, or which sort of variables to retrieve from the storage, and which calculation to perform each time. So it really was kind of, or would have been if it had been built, a general purpose computer. Charles Babbage presented this idea at the time, because it wasn't built, to various people in various places. One of the places was in a university in Turin, in Italy, and this, at the time, I think he was a young officer in the Italian Army Corps of Engineers, Luigi Menabrea. He was very fascinated by this, and he wrote a paper about this idea of Babbage's, which was published in French. And at some point later, Ada was asked to translate that into English, which she did. So she translated Luigi's paper, but she also appended a set of notes, which are about 3 or 4 times the size of the actual paper. And it's in these notes that we find sort of the really interesting comments. So, as I mentioned, there is a description in there of an algorithm for calculating Bernoulli numbers, if I remember correctly. But he also makes a lot of remarks about the sort of the potential and the generality of this analytical engine. And I'd like to quote some of them, especially the first one, where he writes that in studying the action of the analytical engine, we find that the peculiar and independent nature of the consideration, which in all mathematical analysis belongs to operations, as distinguished from those objects operated upon and from the results of the operations performed upon those objects, is very strikingly defined and separated. So effectively what he is saying is that computer science, which is the science of the operations rather than the things that you are operating on, is a science of its own. And in difference to Babbage, who always thought of this analytical engine as a numerical calculation device, he points out that you could apply operations to things other than numbers. In fact, it could apply to anything as long as you can find a set of operations that sort of behave like the operations that we do on numbers, then we can actually apply this analytical engine to any sort of information. He also points out sort of other things like how you use you need to use intermediate variables in certain calculations, how you define loops, that loops are defined by their terminating condition, not by the number of iterations, and so on. And a loop is indeed a loop, even if it iterates 0 times, is one of the things that he says, which you would know if you have written while loops. Sometimes they run 0 times. Finally, there's a famous passage at the end, which is kind of interpreted as a saying that artificial intelligence is impossible. The analytical engine has no pretension whatever to originate anything. It can do whatever we know how to order it to perform. So she's saying that although the engine is clever, it can't really make up stuff of its own. Now, whether that or not is true or not of modern computers is a sort of an open question, I guess. Anyway, so that about Lovelace. Now, for the rest of this lecture, we're going to talk about hashing again. So we're going to rehash what we said at the last lecture about hash functions and expand a little bit on their uses, and then look at how they might be used in implementing certain abstract data types. So to recap, hash function is pretty much just a function. It's a function that maps some set of keys to values within a prescribed range. So typically to numerical or at least ordinal values, we should say. And we require a hash function to be deterministic, at least within a given run of a program. So at least within a run of a program, whenever we hash a certain key, we should get the same result out. Now, for a hash function to be useful, it needs to have more properties than that. And the most important one is that it will distribute for a given population of inputs. So population of inputs is not necessarily the same as the set of all possible inputs. It's the set of inputs that you sort of expect to actually see in practice, whatever that means. So for a given population, it should distribute the hash values of the elements of that population evenly within the prescribed range of numbers or ordinals. Sometimes we talk about a perfect hash function, which gives a unique value for every input. Of course, a perfect hash function does not do any sort of real compression or reduction, except for perhaps removing some sort of redundancy of representation in the original values. There is also, we could also talk about cryptographically secure hash functions, which is another sort of category which have other requirements, but we'll mention those in a little bit later. All right, so what do we use hash functions for? Well, they have a lot of different uses in computer science and other related areas. So the one we will explore today and in the next lecture is implementation of a hash table. You might have heard of hash tables. So a hash table is a way that you can implement the abstract data type of a set or a mapping. And we'll see a little bit why this is a good way to implement it. There are other uses, so checksums, for example. So checksum is something that you calculate from data in order to verify that the data is in some way error-free or correct. So one of the early uses is in, and we'll mention this in a bit, is the what's called the Loon algorithm, or Loon. I'm not sure how to pronounce it. He was German. So this was used initially, I think, for credit card numbers. So when you have a credit card number, typically the last digit, and this applies to many other numbers, is a checksum. So it's a value that is calculated from the other digits. And the property that you're looking for here is that if you have an error somewhere, so let's say if you copy your credit card number down from the card onto a paper by hand, and you make an error somewhere, then the checksum will be incorrect. And it sort of doesn't matter if you make an error in the actual number or in the checksum itself. As long as you don't make too many errors, the checksum calculation should be able to then tell you when you repeat it that this number is incorrect. It doesn't tell you what the correct number is. To do that, you need something more advanced, error-correcting codes. One of the, actually mentioned here, early famous examples is Hamming codes, which I believe are still in use today for checking for bit errors in computer memory. But initially, error-correcting codes were used for data transmission. So where you send data across telephone wires or something like this, or in radio, where errors in electrical errors in your reception or in disturbances in the wires cause sometimes there to be errors in the transmission. And the purpose of an error-correcting code is to detect when errors have happened and possibly also to allow you to correct errors. So the original Hamming code is what's called a 7-4 code. So that means it has each code word consists of 7 bits, and 4 of those bits are data, and the other 3 are the checksum. And this has the property that as long as there is only one error in those 7 bits, you can calculate you can detect that there was an error, and you can calculate what was actually the original code word that was sent. So these work well when you have sort of sparse error, when it's unlikely that you have more than just a single bit error in each batch of 7 bits. So another sort of use for hashing is compression, or what you might call naming. So typically the hash of any sort of object or data is going to be much smaller than the object itself. So we can use that as a sort of label for an object. And if the hash function is good, so it distributes nicely, then the chances that 2 different objects will have the same hash value is very small. So, for example, I'm not sure if you have looked at the Git log in either in GitLab or maybe in IntelliJ. You can see that there's this long, for every commit, there's a long cryptic alphanumeric string. That's a hash of the commit. So Git takes essentially all of the changes that you commit and hashes all of it and comes up with this string of, basically hexadecimal number. And it uses that to identify that commit. And I'm not sure exactly of the details, but there is kind of an operating assumption in Git that this identifier for the commit is unique, at least within the history of the project, within each repository. There might, of course, be sort of different repositories where you end up with the same commit hash. And as I mentioned, there's also cryptographic applications of hash functions. So for a hash function to be cryptographically secure, it needs to have some additional properties. So it needs to have, well, one is that the hash value should not sort of reveal any information about the object that was hashed, which means that a sort of sufficiently large number of different objects should hash to the same value, because that way you can say that if you know the hash value of something, you don't really know anything about the something. And the other one is that they should be difficult to invert, which means that given a given a hash value, well, you shouldn't be able to actually compute an inverse, but also it should be computationally difficult to construct an object that hashes to a given value. And there's a lot of uses for these cryptographic hash functions, but just to sort of give one example, you can think of something like the digital equivalent of putting something in a sealed envelope, right? So let's say, now I haven't prepared any quizzes for today, but if we're doing a quiz and we're doing it in a more old-fashioned way, you might write down your answers on a piece of paper, put that in an envelope, and then we collect the envelopes. And then once everyone has answered, we've collected all the envelopes, then we can open them and check who answered correctly, or who answered correctly and who answered not. So if you wanted to do that electronically, you sort of have a problem that we can't broadcast your answers without revealing them to everyone else. And we also can't wait and reveal the right answer and then ask you, was your answer right? Because then you haven't committed to an answer before we reveal the true answer. So the way you can do it with a hash function is that you write down your answer in a file or something, you hash the file, and you broadcast the hash value. Then we reveal what was the correct answer, you check your answer against the correct answer, and we can check that you haven't modified your answer because we can hash your answer and check it against the hash value that you published before. So it satisfies both of these properties that you couldn't, you have to commit to something before we reveal the answer, but you don't have to publish what you committed to. One of the early examples of a cryptographic hash function that was in widespread use is MD5. It was invented in the early 90s, 91 I think. It's no longer in use for cryptographic purposes because it turned out to be not secure. So after a decade or so of lots of people scrutinizing it, they came up with quite a few ways to break it, but and it's been replaced by hopefully better cryptographically secure hash functions by now. But it's still used in some ways, for example, as a checksum mechanism. In fact, if you do a commit to, for example, something like the assignment repo, and it fails the checksum, that's because some file in your repo doesn't match what it should be, and what it should be is determined by the MD5 hash of the file. So it's still in use. Another sort of use is which is again, it's a bit like Git, it's about identifying parts. So rsync, which is a system for synchronizing distributed file store or files distributed in multiple places, uses hashing to sort of identify sections of files that are different between the different storage places, and therefore to transmit only the modified sections. So it's kind of used as a form of compression. All right, so with this bit of background, let's go over to abstract data types and in particular hash tables. But we'll start with the abstract data type, which is sets. So hopefully you're all familiar with the mathematical notion of a set. Set is a collection of objects or elements without duplicates and without order. So that means for all the elements in a set, the only thing we know about elements in regards to a set is are they in it or are they not. So we can't count how many times they're in it, we can't say where they are in sequence, it's just are they there or are they not. So when we talk about data structures implementing a set, the kind of operations we want to do is, well, primarily to add, check, and remove. Well, of course, we need to create a new empty set as well. But mainly the operations are to add elements to a set, to check if something is in a set, and to remove them. And then using that, we can, of course, implement standard sort of set operations like intersection, union, difference, symmetric difference, and all of those things, subset checking. So we'll be implementing a simplified set, of course, same as when we talked about lists. There is a set interface in the Java standard library. There are good, efficient, hopefully bug-free implementations of the set interface in the Java standard library. So again, the reason why we're going through this, implementing our own version of hash sets and binary tree sets, is to kind of to see how things work, to see how things are done, and to understand how to use hash functions in this case. So our simplified set interface just has these basic operations: add, contains, remove, and also checking the size, so how many elements are in a set. So let's go and find it here. So yeah, so here's our set interface. And as usual, when we talk about implementing these, we'll start with defining some tests. I've written down tests already here. So we have sort of, what do we have, three tests here. First one is just to create an empty set and then add things and check that the size is what we expect it to be. So we create an empty set, it should have size 0, we add 3 things, it should have size 3. Then if we add things that are already in the set, the size should not change because sets don't have duplicates, right? And then we check contains, so we add things and then we check that it contains the things that we have added and it doesn't contain the things we haven't added. So these are all done on strings. And finally, we test remove. So we test that we add a few things. If we remove something, then the size changes, and it is the thing we removed is no longer in there according to contains. And if we do we have did I put that one in? Yeah, removing something that is not in the set should not change the size of the set. So, so that's sort of how our set interface looks and how we're going to test it. And we'll be talking today and next lecture about 2 different ways of implementing it. So let's come back to here. And the first one is hash tables. But before we go into hash tables, we need to take a moment to talk about equality. Not in any general sense, but specifically in Java. What does it mean for things to be equal in Java? So there are two different ways that you can test equality in Java. So I'm sure you've used the double equal sign, the equality operator. So what does this do? This compares, when you do equality in this way between objects, it compares references. So what that means is that only an object will only be equal to itself under this sort of double equals operator. But so remember that in Java, all objects are in one step, in one way or another, inherits from the root object, Java lang object, and this sort of root class defines a method called equals, which takes another object and returns true if this object equals the other object. And the intent is that this can be used to define class-specific semantic equality. So something sort of more meaningful than just looking at references. So the default implementation in the object class is just the standard equality, so just reference equality, which means that when we talk about the most general class of objects in Java, objects are only equal to themselves and nothing else. But we can override this when we define subclasses to provide some better way of defining equality for certain classes of objects. So let's look at just a little example of this to see how it works. So so here we just have two different strings. They're both initialized to the same value, and then we check, are they equal according to the sort of equals operator? Are they equal according to the equals method? And we'll also look at the hash codes. We'll come back to talk about hash codes in a moment. So let's run this and see what happens. So here we see that both types of equality is true. But that's just because the compiler is clever enough to notice that this is a constant string, so I'll just use the same string for both. So in fact, if we do this, and instead of just assigning P2 here the same string, we create a new string and just give it the same value. And we run this, need to do a build. Then what you can see is that the double equals gives false, because now we have two different objects. So references are not the same. But because they are two strings and they contain exactly the same characters, and the string class overrides the default equals methods to provide, as you would expect, an actual string comparison between strings. So the equals method still returns true. Whereas, of course, if we change this to be something different, so John II, there ever was such a person, then the equals method, of course, will also return false. So to show this with, so all of the, I shouldn't swear to it, but I think all of the classes in the Java standard library implement some sort of reasonable equality measure that is appropriate for the class. So if we talk about strings, they would compare characters. For numeric classes, they would compare things numerically. Not always in a way that you would expect. I'm not sure what the collections do actually. Lists or sets and things like this, how they implement equals, but you'd have to look it up and double check, but I would imagine that they probably implement a reasonable type of equality. But just to see how this works, let's have a look at an example of something that is not just a basic sort of or predefined Java type. So we're going to use the class person that we wrote sometime back in the first half of the semester as just an introductory example of how to define a class with fields and methods. So remember that a person has two fields. It has a name and an age, which is string and an integer. So here we create two different persons that are the same. So both of them have the same name and the same age. So if we run this, well, what we see is that reference comparison returns false, of course, because we have created two different objects. The equals method also returns false, and that's because the class that we have defined here inherits the default equals implementation from the root class object. So it's just doing a reference comparison. But we can change that. So let's go and have a look in here. Now we already have an implementation written here, so I'm just going to uncomment it and then talk a little bit about it. So we can define the equals method. Note that the equals method takes as argument an object of type object. So it doesn't take a person, which means that the first thing we have to do is to check, is this other object of the same class as me? Or you can of course define an equals method that accepts arguments of other types than the same class. It's up to you how you define it. But here we're just checking that the other is a person. If it's not a person, then we will return false, because we don't consider any object that is of a different class or subclass to be equal. And then if it is a person, the other object, then we will simply return true if the name matches and the age matches. So this is our implementation of equals. And if we now go back and run the equality test with these two people, we will see that, again, the reference comparison, of course, is false because they're two different objects, but P1 equals P2 is true, because we have now implemented a notion of equality for this class, which means that two people with the same name and age are considered the same. Now, of course, if we change it to something else, let's say we have an old John and a young John, then they will no longer be equal. The other thing that all Java objects have is a method called hashcode. So Java allows you to hash any object. And again, the root class object implements a default hash function, which you can override to provide a class-specific hash function. Now, there is a requirement on the hash function, which is that two objects that are equal according to the equals method must hash to the same hash value, which means that whenever you override equals, you probably have to override hash code as well, because the default implementation does not take into account your custom notion of equality. So if you just leave it with a default hash code, then your class is likely not to work in things like hash tables. Well, it will still compile, it will still run, but it will give incorrect results if this requirement is not satisfied. So coming back to our person example, I just uncommented here also our implementation of hash code. So here we take the hash code of the name. So again, remember, all objects have a hash code method, so we don't have to come up with how to hash a string. We just use the string class's hash code method, and then we just add the age. So the value returned by hash code is an int, and because the age is an int, we can just add it. Now, is that a good way to hash people? I don't know. Maybe it's not the best way, but at least it satisfies the requirement of be matching with equality. So any two person objects that have the same name and the same age, because they would be equal, will also have the same hash value. All right. So with that sort of side remark, we can go on to actually talk about hash tables. So a hash table stores keys using a hash function to map those keys into table entries. And we can either just store keys, which means that the only property we have then about the keys is are they in there or not. So that's kind of how we would implement a set. Or we can associate keys with values, which is how we will implement a hash map, which we'll do sometime next week. Now, because hash functions are not always perfect, and because the size of the table is limited, we will have hash collisions. So that means we will have different keys that hash to the same value, which means we sort of have to store them in the same entry. So there's broadly two different ways we can do this. Either we store a list or set or whatever we choose of different keys for each entry in the table, which means that the table doesn't map one entry to one key, it maps one entry to a subset of the keys stored in the table. Or we can do what's sometimes called open addressing or open hashing, which means that we only use the hash value of a key as a starting point. So we find the table entry where it should be, but if that's occupied, we then somehow search for the next empty slot. We could either just linearly step through and go, is the next one empty, is the next one empty, is the next one empty, and so on. That's more complicated to do, and in particular it will be very complicated when you start to remove elements. But it has some uses. In particular, it kind of has an advantage for in certain use cases with large hash tables because of memory locality. Because when we try to search for a value, we're generally only going to be searching in a very small region of memory nearby where the element should be, whereas with a list, we're going to go to the table, find the entry will have a reference to a list, which might be anywhere else in memory, and if it's a linked list, its elements might be all over the memory, so we have kind of less locality. But that's a sort of consideration that only really plays in if you're doing lookups in very large hash tables. So I think we'll only be looking at the chaining approach. So the idea of the chaining approach to hash tables is really just like a bit like an index, or you can think of it like the labeling of the shelves in a library, right? The labeling just tells you that this shelf contains all authors from A to F. And then you have to go and actually scan the shelf to find a specific title or author that you're looking for. In the library modulo people messing it up, books are sorted. We don't have to have things sorted in here. It's kind of a design choice. We could choose to have the list of entries within each bucket, as we call the entries of the table, sorted or unsorted. Unsorted gives us faster insertion because we can just add an element to the list. We don't care about sort of figuring out where it has to go in the list. Sorted gives us faster lookup because when we're looking if a key exists in the table, well, we hash the key to its hash value, we find a bucket, but now we have to do a search in the list to find is this key actually in the list. If we have a sorted list, we can do a binary bisection search, which is faster than a linear search. But on the other hand, it's a bit more complicated. So we have some design choices. But let's look at just how we implement some of the basics of this. So here's just the sort of beginning of our implementation of a hash set. So this implements the set interface, so which means we have to create the add, remove, contains, and size methods. We need a constructor as well. No, not hash set. Nope, I'm going to call it hash set. And I don't know exactly what it's going to do. And we need some fields. So we need a table where we're going to store things. And because we want our table to be efficient to index, so we want to not have to search through the table to find a given index. So we're going to use an array for the table. And because we want to use the chaining method of storing, we need an array of lists. So I guess we will be using something like the standard, let's say, util linked list or array list, linked list. Let's use a linked list. So that means our actual table will be an array of linked lists of the target type. Let's call it table. So that's our table, and kind of, I guess, similar to how we did with the link when we implemented the linked list. I think it's convenient to, if we store in the hash table class, how many elements are in the hash set. Even though we could calculate it by just going through the table and then counting the size of all the lists. But I think it will be convenient to just store, we'll call it, I don't know, n entries. What do we need to do when we initialize a hash set or a hash table? Well, we need to allocate an array, and we need to, at some point, we need to also allocate linked lists to the sort of elements of this array. We could actually, we could choose to leave it null, so that would give us a more economical representation of an empty set. But it's also going to make it a bit messy to implement the add method, because we're going to have to go and look everywhere if things are already allocated or not. So we may as well allocate the table. So we'll say the table is and we need to initialize it to some size. So we need to pick a size, a default capacity for the hash table. We could define a constant, just say, alright, final int default capacity 20, or whatever number we choose. So that allocates the table, the array. Do we want to fill the array with lists as well? Maybe we do. Yeah. All right, we'll do that. Then we go. There we go. So we allocate the whole thing. It may be a bit wasteful, but it will make the add method easier to implement. And then we'll just set number of entries to 0 because the table is initially empty. Okay, so now to add something to the table, what do we need to do? Well, first we need to figure out which bucket is this element going to be in, right? And to do that, we will hash the element, which we will do using the element's hash code, right? And then we just need to add it to the list in that bucket. Or rather, we need to check if it's already there. Because if it's already there, then we shouldn't add it, because this is a set. It doesn't contain duplicates. So maybe what we'll do instead is something like, what should we do? We might have use for this somewhere else. Yeah, let's separate out this into a little find function. Private G find. Oh. Okay, this is a bit funny, but so we'll use this one internally to find an element in the table, return null if not present, something like that. That's putting out a bit of an assumption here, saying that we're not going to store any nulls in our table, but that's okay actually, because we can't hash the null value anyway. So maybe what we'll do then is just move this into the find method here. So we hash the element, and then we do for, I guess we can do, okay, what should we do? Now we'll do an iterate. So remember that we index the table to get the list of elements that are in that bucket, and then we iterate over them, and we say if this element in the bucket equals the element we are looking for, then we can return it. And otherwise, if we get to the end, we return null. Right. So that's our little sort of internal find method. And so with that, we'll then have to do, explain in a second why I'm changing this here. We'll pass the bucket there as a parameter instead. And we'll calculate it here, and we'll go t find bucket. So something like that. So so the reason why we're hashing it here and passing the bucket index to the find method instead of hashing in the find method is that we need to use it twice, right? If it's, we need to use the bucket index again. So if we hashed it in the find method, we would have to hash it twice. Now, the reason we might think, well, why do we care if we hash it once or twice? But because we don't know anything about the elements that we're storing, and we don't know anything about their hash code computation. It could be something really computationally expensive to hash those elements. So let's just try to be cautious and be a bit economical and not hash things more than we actually have to. Could be a bit unnecessary. So the other thing we're doing here is just that, well, we're checking if the element is there. If it's not already there, so if the find method returns null, then we just take the list that represents that bucket and we add the element. Okay, so that's our add method. Now, now, can anyone see what the bug in this is? What's the error here? Yes? Sorry? Yeah. Sorry, I'm not sure if I get what the what you think the problem is. So we created an array of linked lists. So we added linked lists to all of them. So all of the table entries are linked lists. But how big is the table? It's whatever size we set it to be, right? We set it to, I think, 20 or something like that. But here we're just taking the hash code and using that to index the table. So the hash code is an assigned integer. So it can be anywhere between, what is it, plus or minus, is it 32-bit, 2 million something. So if we run this, we will probably see an array index out of range. But we can try it and see if my guess here is correct. So so remember that the first test that we do, we need size as well. Actually, we haven't updated size either, so that's another bug. Alright, so what we need to do, if the element is not already in the bucket, we add it to the bucket and add 1 to the number of entries. And we need to implement size as well. Where do we have size? Return the number of entries. There. So now we have implemented add and size, which is enough to run the first test. The first test only tests add and size. So we'll run our testing here. Hopefully after building succeeds. I see. Thank you. I see what you were on about. This is Java tripping me up again. Right. So we're not allowed to create an array of generics. So how did we fix this? We put object in here, or something like that. No. We create an array of objects. Right. That's how we do it. If I remember, we create an array of objects and then we cast it to an array of linked lists. Okay, let's bracket that to be sure. Is that going to work? we haven't actually updated the test class to use the hash set. It was just using null. Alright, so now is that going to use the right hash set? Yep, it is. Alright, so that should take care of that. So again, this is the same as we did for the list implementations. The test class has a method to create an empty set in this case, where we just change which implementation we're using. So that's our generic again. This is our array of generics that is messing up. Is it because of how we bracketed it? Is that the one that's failing? Right, because it's trying to cast the object to linked list. We want to cast as the array. How did we do this before? Go back and look at this. Right. Yeah, okay, we did it like that. Let's see if that works. Let's see, what's the, so the table is an array of linked list. Now it's still complaining. So it builds. No, it's still not liking that. Let's start with separating these just to see. No, it's not a linked list. Alright, we'll just do a little temp array there, and separate that out, and just to see what that's telling us. So it worked okay here. not liking this. So which one? No, if it's it's not complaining. Oh, hang on. Yeah, okay, now we got a different error, which is the one I was expecting. Alright. So, yeah, as I was saying before, we're just using the raw hash codes to index the table, but the hash codes range way outside the size of the table. So, the usual way to do this is just to do a mod. So we take the hash code modulo the size of the table, so, or the capacity, so table length. That should take care of it. Can it still do negative? Does mod give negative values? Alright, if we're going to be that complicated, let's move all this out to a separate method. What do we call it? Get bucket. So okay, no, print. Okay. Right, we'll start with getting just a hash code. Why do you know? And I guess if we have to account for negative, then we'll do, we'll just convert it to positive. If it's less than 0, then just multiply with -1, and then return mod capacity. So yeah, except now half the screen has disappeared. And this will still be returning an int. Alright. Let's see if we're happy with that. Alright. Now we got through at least the first test, which is what we were hoping to do. So creating a set, adding elements, and checking that the size is correct. So with that, we can try to fix the other part, so contains and remove. Contains is fairly straightforward given what we already have, so we just do exactly what we did in add, because in add we already check is the element already there. So we do get bucket for the element, and then we do find the element in the bucket, and we simply return key is not null. Oh, keep using key. Should use the variable found. There. So that should be a way to check contains. Remove is maybe a little bit more complicated. Where do we do that? Remove. Should be here. Ah, here it is. So what do we need to do in remove? Well, first we need, same as in add, we need to check if it's already there. So you just start off with the same thing. We need to find out which bucket. Get bucket for the element. And then we need to check is the element in the list, and if it is, we need to remove it. Now, do we remember how you can remove things from a linked list? Not necessarily how you implement it, but what the interface allows us to do. Yeah, I think we need to have the index right. We'll do our usual and go to find some API documentation. Standard list interface actually probably has a contains method, so we didn't really need to implement find. But it has an index of, so we can use that to find or to get the index of something that is in there. Actually, it returns -1 if not there, so we could use that to simplify life a bit. And we can also even remove an object. What is this? Optional operation. Alright, we'll try with remove object and see if that works. If it does, it's all good. Otherwise, we'll have to do something more complicated. So if that works, then we should just say if where's table bucket contains element, then then we need to remove it. And reduce the size. So that should work if those list methods do what we hope they do. So we'll try that and see how it works. Alright, so that's passing all the tests, so that's now correct. However, let's come back again to this sort of the slightly more abstract view and say, why are we using hash tables? So our hash table here is just an array of linked lists, which means that we hash an object, we get its bucket index, and then we go and search a linked list. Why are we doing this? What's the point? Why don't we just have a linked list and search the linked list? Because the hash table allows us to break the list up into smaller lists, which means that we should do less searching, right? That's the point. The reason why we do this is that if the table is big enough, and if the hash function is good and distributes values evenly across the tables, then all of the lists in the table will be small. Ideally, if we make the table really big and the hash function is really good, there should just be one element in every list, which means we shouldn't have to do very much searching. So that's the purpose. But are we actually achieving this with our current implementation of the hash table? Well, it depends on how much we're adding. So what we can do, I thought, is we can have a look at how the table behaves. Let's say we'll do a little method here. Probably private doesn't matter. Call it void check stats, or something like this. So we'll do a little thing where we'll see, we'll check what the stats of the table are, how it's behaving. So one thing we want to look at is the, and we'll just print out these numbers. No, doesn't do that. System out print line. So we'll print table station. The ratio of number of elements stored to capacity of the table. If we were allowed to print a ratio, I'm not sure. So we'll take number of entries divided by the table length. I think that's called utilization rate. And the other thing we can look at is what is the maximum or average or other indicators of the sizes of the linked lists that we have. So we'll call it, let's say, max length 0, sum length 0. Sorry if I'm sort of half the time using Java naming and half the time C++ with underscores. One can go back and clean this up a bit later. So we'll just iterate over the table, table length plus max operator. Doesn't seem like it. If table I, it's called size, isn't it? Size is greater than maxlen, then size, and alright, so we'll do something like this, and then print out max bucket length is maxlen, and I mean should be again the sum divided by table length. Right. So we'll do something like that, and we'll just put a call to this checkstats function at the end of at. So every time we add something, we look at, well, what's the stats of the table now? We can run through the tests again. But while that's building, let's go and have a look here. Because these tests are not really going to be that interesting with respect to sort of testing, stress testing the table implementation, because the most we add is like 5 or 6 elements. But we can just see that it's working. So we'll use another testing method here. I'm just, instead of putting it here, I'm just going to copy it over into here and put a main just in here, and here, and stress test. Okay. Hang on. Right, we need to make that one static. And then we'll use so what this will do is just read a file which is assumed to contain a bunch of strings, one per line, and just add all the strings to the set and see what happens. So I think I have a data file here somewhere in resources. Well, we have multiple. Okay, that's not in there. Ah, right, because it's in there. Instead, there's a duplicate there. Okay, so it's going to be called, where is that? So it's in words, plants. So that's a list of random plant names. I'll look at it. Yep. So it's not very big. It's about, what is it, 271. So it's not a particularly big set, but we'll see what happens with the hash set as we do this. Then we have to go here and run hash set main. this works. Actually, it's probably not going to work. So, or did we already? Oh no, we already had an import here for those things. Okay. All right. So what we can see is that, well, at the end, after we added 271 names, table utilization is 13. So that means the number of elements stored is 13 times the capacity of the table. The maximum bucket length is, or the maximum length of one of those lists is 19, the mean is 13. Okay, so the hash function is good. It's actually distributing quite evenly since we're getting, but the table is just too small, right? So in order for a hash table to work efficiently, as we keep adding and checking things, we have to dynamically grow the size of the table, the same way, in a way that we did with the array implementation of a list. So let's see. Let's go and have a look at the reasoning behind why you would do this. So the idea is that if we can control the size of the buckets, then we have effectively lookups in constant time. Right? If the size of every bucket is a maximum of 5, then we know that we have to do no more than 5 comparisons in order to test one hash computation and 5 comparisons in order to test if an element is in the list or in the set. So we're not exactly going to control the bucket size directly, because that's also a function of the hash function, right? So we could create an enormous table, but if we have a really bad hash function, we're going to end up with lots of elements in the same bucket anyway. So, but we'll try instead to control the utilization rate. So if we have a good hash function, then the bucket size should be roughly even, which means it's proportional to the number of elements divided by table size. So if we keep the utilization rate down to something like 1 or maybe 2, between 1 and 2, then we should have very short lists. And in order to do this, same as we had to do with the array implementation of lists, what we will have to do is at some point we'll have to allocate a new array and copy over the contents from the old to the new. And in the case of the hash table, this will be a bit more complicated because we can't just copy the buckets. We will have to actually go through and rehash every element that is stored to find out what is its new bucket going to be, and then put it in the new bucket. But if we don't have to do the rehashing too often, then we can still end up with what's called amortized constant time. So, which means that if we do a number of add and contains checks, then the average time sort of for each one of them will be constant. Some of them will actually take a lot longer, because every time we do an add and we have to do a rehash, that's going to be time proportional to the size, the number of elements already in the table. But if we avoid doing this too often, then we get on average constant time. And this is kind of an illustration of the idea. The idea is the same as we did with the array list implementation, is that every time we need to increase capacity, we double the size of the table. Because then the amount of work that we do every time is proportional to the number of elements we have already added, but we're making sure that we're going to have to do only constant work for at least as many elements into the future. And that's why we end up doing sort of on average 2 units of work, or if you can think of it as 2 calls to the hash code functions every time we add it. So practically, how would we do this? Well, we already put our little hook here, which is the check stats function. But instead of check stats, let's just make a new one. And actually, it probably should be private. We'll call it rehash if needed, or something like this. Maybe we should split this into one that actually does the rehash and one that does if needed. Not so. Can we get a double out of? So we calculate the utilization rate and we check that against some threshold. Let's say if util rate is below 1 maybe, then we don't need to do anything. So we're just going to return. And otherwise we will need to then do a rehash. And to do a rehash, we first have to go and allocate a new array, which is an absolute pain, but let's find out how we did it. Right. So we needed to allocate a maybe we don't need that term construction. So we're going to allocate a new table, and what size are we going to make a new table? Well, we're going to make it the twice the size of the current table. Right? And we're going to initialize the new table with empty linked list. This is just standard stuff. Yep. And then we're just going to iterate over the elements of our current table, add them into the right place in the new table. To iterate, we'll need to do, again, we'll need to do a double loop here. First we're iterating over the buckets, and then we're iterating over the lists within the buckets. Table length, B++, and we do for element in our existing table bucket B. And here we'll need to do again, that's a bit annoying. We'll need to do the whole get bucket thing, but we need to do get bucket on the new table, which means we need to pass length as a parameter. Pass the size as a parameter instead of hard coding it in there. So that we can do get bucket, which means we need to modify every call to get bucket. Again, we're going to do it there, this table length. Right, so in here we can now do new bucket, which is going to be get bucket for the element and the new table size. Right. New table length. And then because we know that this element is we already know that it's not in the new table, so we don't have to do a check, we can just add it. Sorry, do you want? We could if the new table was an instance of hash table, but it's not, right? It's just, so we'd need a double layer of kind of abstraction where we have, because we're doing this inside an existing hash table object. Yeah, I could create another hash table object, call add on it, and then just steal the array from that hash table and use it as this one's. We could do that. Either way, it's not particularly neat. And in fact, here, actually, we, and this is a little bit wasteful because we don't actually need to hash the element. We already know what its hash code is. Or, incorrect. No, we don't know what, we know its bucket, not its hash code. So no, we do need to hash it. But anyway, we'll just finish off this one. So because the idea here is to see what effect it has on the sort of sizes of the table. So new table, new bucket, which is a linked list, and we're going to add the element there. And it's complaining because I have not, I've done loads of syntax errors here. And haven't defined a type for that thing. Now, why is it complaining about that? Alright, now if we have done that right, we should have added everything to the new table, and then we'll just replace table with new table. So that should take care of that. So if we have done this correctly, we can now do, every time we do an add, we do rehash if needed, and then we can print some stats afterwards. Right. What's it complaining? Oh, actually there are multiple errors here. All right. Yeah. And also we have some calls to get bucket that we haven't fixed, which is in here. Yep. And there should be another one somewhere here. Alright. So let's try this and see what happens. Alright, okay. Why are we getting 0 here? Is that just a printout thing, or is it actually losing stuff? Alright. That might just be a printout thing, so we're going to try to do length and just force that into a floating point number. Not sure if this will actually do the trick. Same with the mean. It's still coming up in 0 now. Alright. Well, it does appear to be working, at least in the sense that the maximum bucket size sort of stays. It still grows a little bit. But we can see actually sometimes it goes down as well, right? So we have max bucket size of 4 here, and then at some point it drops to 3, and then it sort of increases again until the next time we do this. Does anyone remember how to force Java to divide 2 integers and get a float? Is it enough to cast the inputs? Yeah, so if we cast this one to a double, or maybe the denominator, I don't know if it matters which one, something like that. I guess we have to do the same for the mean length as well. We'll see if that actually prints something that makes sense. Alright, yeah. So, alright, so here we can see that the sort of the utilization is keeping somewhere, and we haven't printed when we do a rehash, but you can see that sometimes the utilization rate drops. So here we have a 0.9, and then a little bit later it's dropped to 0.5 again, which is kind of what you'd expect since we doubled the capacity of the table. Alright, so I guess that's enough for today, and then Monday next week we'll look at an alternative implementation of the set abstract data type.